Hey, I am Mrs.Compile, and today we are going to break down how data actually travels across the internet. Packets, routers, and the postal system you never knew existed. No boring lectures, just how it actually works. So, let's get into it. So, we know your browser finds the address with DNS, Domain Name System. We know it sends a polite message using HTTP. But we have been glossing over something massive. How does that message actually get there? Like physically? Your laptop is in your bedroom. The server is in the data center in Virginia. There's an ocean between you. How does the data cross it? It doesn't fly. It doesn't teleport. It gets broken into tiny pieces, put it into digital envelopes, and sent through a chain of routers and cables until it arrives. Then gets reassembled at the other end. It's a postal system. And honestly, Royal Mail could never. This is TCP and IP. And it's the actual plumbing of the internet. So, let's open it up. Now, imagine you need to send a really long letter to someone. Like your entire dissertation long. You could try to send it as one massive scroll. But the post office would look at you like you have lost the plot. And if it got lost in transit, it's gone, the whole thing. So, instead, you would split it into smaller letters, like page 1 of 47, page 2 of 47, each one numbered, each one in its own envelope. If one gets lost, you only need to resend that one page, not the whole thing. That's exactly what the internet does. Every piece of data you send, like a web page, an image, a video call, gets broken into small chunks called packets. Each packet is typically about 1500 bytes. That's roughly 1.5 pages of text. Not very big. And here's the clever part. Each packet doesn't have to take the same route. Packet 1 might go through a cable under the Atlantic. Packet 2 might bounce through a satellite. They all take whatever path is fastest and least congested at that exact moment. It's like if you and your friends all left from the same restaurant, each took different routes home, and somehow all arrive within seconds of each other. Uber drivers could never. Every packet has two parts, the header and the data. The data is the actual content, a little chunk of the web page, a fragment of an image, a piece of a WhatsApp message, the good stuff. The header is the envelope. It contains everything the internet needs to get this packet to the right place. Source IP address. Where the packet came from. Your computer's address. Destination IP address. Where it's going. The server's address. Sequence number. Which piece of the puzzle this is. So, the other end knows to put packet 3 after packet 2, not before packet 1. Without this, your web page would look like someone put it through a blender. There's also a TTL field, time to live. But this doesn't mean the packet dies dramatically. It's a counter that goes down by 1 every time the packet passes through a router. If it hits 0, the packet gets discarded. This stops packets from bouncing around the internet forever like a lost ghost on the tube that never gets off. Now, packets can get lost, cables get damaged, routers get overloaded. The internet is not a perfect place. It's a bit like the Northern Line. Really. Mostly works, occasionally chaos. So, we need a system that guarantees delivery. That system is TCP, Transmission Control Protocol. TCP does 3 things. First, before sending any data, it establishes a connection using something called a 3-way handshake. And yes, it's as formal as it sounds. Your browser says, "Hey, can we talk?" That's the SYN. The server says, "Yeah, I'm here. Can you hear me?" That's the SYN egg. Your browser says, "Loud and clear. Let's go." That's the egg. It's like when you phone someone and you both go, "Hello, hello, can you hear me?" "Yeah, I can hear you," before any actual conversation happens. Second, TCP numbers every packet and the receiver confirms they arrived. If the sender doesn't get a confirmation for packet 7, it sends it again. No packet left behind. Unlike that group project in uni where Dave definitely left you behind. Third, TCP controls the speed. If packets are arriving too fast and the receiver can't keep up, TCP slows down. If things are smooth, it speeds up. It's like a DJ reading the room, adjusting the pace based on what the crowd can handle. TCP handles the reliability, but the actual navigation, getting each packet from point A to point B, that's IP, Internet Protocol. Every router on the internet has a routing table. Basically, a massive set of directions. When a packet arrives, the router checks the destination address and says, "Right, the fastest way to get there from here is through that router over there." And then the next router does the same thing. No single router knows the complete path. Each one just makes the best next decision. It's like asking for directions in a city where nobody knows the full route. But everyone knows which street to send you down next. Somehow, you always get there. And sometimes the path changes mid-journey. If a cable goes down or a router gets congested, packets get rerouted on the fly. Packet 1 might go through London, packet 2 through Amsterdam, packet 3 through Dublin. They all arrive at the destination, get reordered by TCP, and the user never noticed a thing. You can actually see this happening. There is a command called Traceroute that shows every single hoop a packet takes. We will run one in the demo. Now, theory done. Let's watch data actually travel across the internet, hoop by hoop. Let's run a traceroute to google.com and see every hoop along the way. Look at that. Each line is a different router my packet passed through. You can see the IP addresses, the location hints, and the time it took at each hoop. My packet just traveled through multiple countries in milliseconds. That's genuinely wild when you think about it. Some hoop shows stars instead of times. That just means that router chose not to respond. It's the introverted router. Still does its job, just doesn't want to chat. Now, let's try ping, the simplest possible TCP IP test. Each line shows the round trip time. My packet went from Bristol to Google server and back in about 15 milliseconds. That's a round trip to probably mainland Europe and back while you were deciding whether to have tea or coffee. So, to recap, your data gets broken into packets. Each packet gets a header with the address and sequence number. TCP makes sure every packet arrives reliably and IP routes each packet through the best path available. At the destination, everything gets reassembled in order. It's a postal system that delivers billions of letters per second, never loses anything permanently, and does it all in milliseconds. And it was designed in the 1970s. Genuinely one of humanity's greatest engineering achievements. And it doesn't even have a marketing team. Next episode, we are talking security. Because all this data flying around the internet, how do you stop someone from reading it? How does HTTPS actually keep you safe? That's the bouncer at the door. See you there. And that's TCP IP sorted. If you learn something new, do me a favor. Smash that like button. Share this with someone who would find it useful. And subscribe so you don't miss the next one. I'm Mrs.Compile and I'll see you in the next one.